So we had been looking at... Oh yeah, we had been way back, sorry now. Okay, so we had been looking at interframe compression and how one might reuse information from a previous frame to build the current frame. And the difference between the frames might actually be quite small, so we can exploit that. And I had been talking about motion compensation, which works if various assumptions hold. So if things move in a plane parallel to the camera plane, everything's hunky-dory. If there's no zooming, things are good. Rotation is bad. Also, the lighting needs to be constant and consistent. So if something moves from a light part of the frame, you know, if someone is there and they move into it under a street light, it's going to be hard to make the lit person from the unlit person. And if someone pulls a rabbit out of a hat, you know, it's going to be hard to make that rabbit out of thin air. MPEG uses iframes and p-frames, or predicted frames, and I believe we saw this already, didn't we? So we have to transmit the frames in an order that's different to hang on. So just to recap, in this example here, frame 2 is built using parts of frame 1, frame 3 is built using parts of frame 2, frame 4 is used by reusing parts of frame 3. And then every so on we have to start again. We usually do that maybe twice a second. Once a second would be pushing the boat out, really. So here an iframe stands alone all by itself, and then frame 6, for example, is made by reusing parts of frame 5. Frame 7 is made by reusing parts of frame 6, and so on. Now, this here now is the really interesting and tricky and head-wrecking part. So if we look at frame 2, which is the current frame that we're trying to transmit, if we compare that with the corresponding block in frame 1, we notice that it's very different. However, the motion compensation isn't any good here, because, okay, it's not where we're looking for it, but it's not a question of it having moved. So when parts of the car move, we can track them and reuse that information to make frame 2. And that's one of the really clever things about video compression. So even if a block moves, we can track it down and reuse it. But looking here in frame 2, it's just not there in frame 1. Nowhere in frame 1 does anything like that grass appear. So you might say, well, we just have to transmit it so. You know, we tried our best, we had to search for it, and it wasn't there. But all of the data that we're looking for, the piece that we're looking for, that is in frame 3, in fact. So we're trying to send frame 2 using parts of frame 1, but it's not there. There's a piece that we don't have. But it turns out the exact piece we're looking for is available in frame 3. Did you get me? This is a bit of a head wreck. I find when people learn this, first of all, it takes them a while to figure it out, what it is I'm saying. Then when they finally understand it, they don't believe it. Then when they figure out the consequences of it, they don't believe it again. It's a tricky one. It's a bit of a head wreck. So, like I said, we're trying to make frame 2. Our job is to transmit frame 2. And we had been hoping to say to the transmitter, to the receiver rather, look, the stuff you're looking for to make frame 2, you already have that in frame 1. But in this case, it's not there. And it's not a question of it having moved, it's just not there. But the stuff we are looking for is in frame 3. And so this brings us to another kind of interframe compression then. We call this bidirectional prediction. So if you can construct a frame by copying blocks from both past and future frames, you can actually achieve quite a lot of compression. Because pretty much everything you're looking for will be in one place or the other. So MPEG also uses bidirectional prediction. We call those B frames. And B frames are very small compared to P frames and I frames. If you understood this, you'd be giving out. So I don't believe you understand me, but maybe when you think about it again later, it will come to you. Now, let us look then at the dependencies between the frames and a sequence of frames. So let's say we start with an I frame, frame 1. And remember, an I frame is a standalone frame. So if someone sent you an I frame in the post, you could open it up and decode it. It would look very like a JPEG. Next up then, we have a B frame. And a B frame works by reusing parts of frame 1 and parts of frame 4. So it uses both a past I or P frame and a future I or P frame. Now we don't allow B frames to reference other B frames, just the quality is a bit ropey. So we don't allow B frames to depend on other B frames. So they use one past frame and one future frame. If we look at frame 3 here, that's another B frame. This is using parts of frame 1 and parts of frame 4. Frame 4 then is a P frame. And it's just reusing parts of frame 1. So the transmitter would be saying to the receiver, look receiver, you've already got frame 1, so take this part of frame 1, this part from frame 1, this part from frame 1, and then, now here are the bits you don't have, here's the parts you don't have. I'll send you those. If we look then at frame 5, that's a B frame, and it's reusing parts of frame 4 and parts of frame 7. Frame 6 is reusing parts of frame 4 and parts of frame 7. And then frame 7 is another P frame. That's just reusing parts of frame 4. So an I frame stands all on its own. It's like a JPEG. A P frame uses a past I frame or a past P frame. A B frame, on the other hand, uses a past I frame or P frame and a future I frame or P frame. And it's the ability to use the future frames that allows them to be constructed with very, very little data. But this has some fairly head-wrecking consequences. So let's say we're transmitting this from A to B. So we send off frame 1, and the receiver goes yip-de-doo, I decode frame 1, and displays frame 1. And we send frame 2. Now, frame 2 says to the receiver, okay, take these parts from frame 1, and these parts from frame 4, and mix and match those to make frame 2. But it's like, duh, I don't have frame 4. I've only got frame 1. So it turns out that in order for the receiver to construct frame 2, it must have both frame 1 and frame 4. Okay, now I see from your faces you understand this. You just can't believe it. So this requires us to transmit the frames in a different order from which they're going to be displayed. So when RTE is sending you, the latest episode of Fair City or whatever, it's actually not sending the frames in the order that you're going to watch them. they're jumbled up, and your set-top box or your TV has to, one, decode them, then construct the frames that it needs to from the bits and bobs all over the shop, and then it has to put them back in order to display them in the order that you'd watch them in. Which is pretty freaky, but it does allow for some fairly impressive compression. You all look like your favorite character has just been killed in some show. Anyway, don't worry, he'll be alive again in 2 frames time. Okay. So the order has to be different. So the frames are transmitted in a different order from the order in which are going to be displayed. So it means that if something is live, it's actually not truly live. It's maybe there has to be a little delay there for the receiver to catch up. Now again, you might send a single group of frames. You might send 2 of those in a second. So it's not the end of the world, you know. It's not a huge delay. This also then has some consequences for noise. So with all of these dependencies, this frame being made from this frame and this frame being made from this frame, if something goes, if a bird hits your satellite dish, or a bird hits your aerial, or if this is going across the web and you lose a packet or something, then the consequences can be significant. So let's say, for example, that frame 4 there was lost. So for that 1/50th of a second worth of data there, actually even less, you know, there was a bird in the way or something, and you've lost that portion of the data. Well, what happens then? If you don't have frame 4, then the frame that was relying on frame 4 is also gone. Because that frame 2 there used parts of frame 1 and parts of frame 4. We don't have frame 4 now, that's screwed. Similarly, frame 3 is now in trouble because it too was using parts of frame 4. Frame 7 was using parts of frame 4, so it now is gone. And also the in-between frames, 5 and 6, are now screwed too. And similarly, perhaps the frames after that. So all you're left with in this scenario is that one iframe. Now, fortunately, in about half a second, or on a bad day, in a second's time, there'll be a whole new iframe coming along and you can start again. You know, providing the bird has gone away, you're sorted. But it does mean that these dependencies between the frames can cause serious problems if a piece of it gets lost. And so when you're watching, if you're watching terrestrial television, you tend to notice it more. I don't see it so much on Sky. I see other things on Sky, but I don't see the frames being lost. And you'll notice too that in the past, if your reception was bad, you'd get all this sort of snowing and all this lines and stuff. But now when you're watching TV and there's a problem with the reception, just all these blocks and bits of hands are where faces should be, and legs are up here and heads are down there, and stuff all over the shop. And there's all this kind of collage, and your receiver has a bit of a panic attack, and then eventually it kind of resynchronizes up with a new iframe, a new group of frames, and everything's back to normal again. But the way in which it degrades is as a result of how it works. It's not very graceful. Any questions on that? So, how about then we look some more at the details of how that compression works forgetting now about the difference between the P frame and the B frame. We're going to look now at the details of how the compression works. So it turns out that video compression is asymmetrical, whereas JPEG, for example, is symmetrical. If you were to compress something using JPEG, each of the steps required is no more complex than the reverse of it. So doing a discrete cosine transform takes as much processing power as the inverse discrete cosine transform, for example. Okay? Video compression, though, takes much longer to compress than it does to decompress. We call that asymmetrical. So decompressing video happens very quickly. It can happen pretty much in real time, which is why if you are looking at a video on your laptop, you can see it. The frames are generated at faster than 25 frames per second, so that you can actually watch them. If you were to take a video and compress it, it might take longer to compress than it would to watch. It typically does that. Now, if you're ripping a DVD, it's actually spending most of its time on the hacking the disk. But if you have just straight video on your machine and you want to compress that, it can take a long time to compress video. And that's because the part of the process where it's looking for the block in the previous frame that might have moved, searching for it, is very time consuming. So if we look here, for example, we've seen this already. We have a block in the current frame that isn't in the corresponding position in the previous frame. But it turns out it has moved. And so if we can find the position of it, then we will be able to tell the receiver where it is. Okay? But the question is where is it? So the location of the target block in the pass frame must be found. And finding that is not trivial. We call that the block matching problem. And I have a little exercise for you. And I'll just go get that. It'll take me 1 minute.